So standard cell potential is the potential produced in the cell when we take 1 molar solutions of electrolytes, and if you keep the pressure as 1 atmosphere, in this case there is no gas involved, so you need not worry about that, and by convention we maintain temperature as 25 degree. Okay, at this condition whatever potential that is appear in the potentiometer, that potential is nothing but E0 cell, called standard cell potential. This not symbol indicates standard. Okay, CEL means cell and E represent potential, so standard cell potential, right? So this is the representation. This is how we represent standard cell potential. Now the students, every time we cannot write cell like this, okay, and we cannot write standard cell potential like this, right? What we have to do, what people did was scientists gave a method to represent the cell on a paper, right? So how to represent a cell on a paper, this is what we are going to discuss now. But before going to see that, let me just brush up how to write E0 cell for this particular cell, Daniel cell. You know very well, in Daniel cell, E0 cell is nothing but standard oxidation potential plus standard reduction potential. This is the sum of these two is what we call as E0 cell. Okay, but what IUPAC said is that let me write this first. E0 oxidation, right? E0 oxidation is oxidation occurs in the zinc electrode. So zinc undergoing oxidation and becomes zinc 2 plus ion. See, zinc is becoming zinc 2 plus. It is oxidation. So this potential is nothing but standard oxidation potential plus reduction takes place at the copper electrode, where cupric ions present in the solution get reduced to copper. Cupric ion becoming copper, this is called reduction reaction. Zinc becoming zinc 2 plus is oxidation. So this potential is standard oxidation potential. Copper 2 plus becoming copper is reduction, and this potential is called reduction potential. Sum of these two potential is nothing but standard cell potential. But I have told you in the last class that IUPAC recommends that we should use only reduction potential. See, here the potential is reduction potential, you need not worry about this, this is okay. But here the potential is given in oxidation, so this is an oxidation potential. What IUPAC recommends is that always represent whatever may be the potential, whether it is oxidation potential or not, you have to represent only in reduction, only as reduction potential. So how to convert? If you want to convert oxidation potential into reduction potential, very simple, change the sign, right? See how to do that. Let me write here. So what I'm going to do, I'm going to convert E0, I'll put minus sign in front. I'm going to convert, actually the potential is oxidation potential, now I'm going to convert into reduction. Reduction means zinc 2 plus becoming zinc, this is called reduction. Okay, if I take reduction potential, then I should put a negative sign in front, plus the reduction potential of the copper electrode. Now both the potentials are reduction potentials. This is as per IUPAC convention or IUPAC recommendation, right? Or I can also write this is E0 cell equal to, I'll write the positive term first, E0 Cu2 plus becoming Cu, this is the reduction potential of the copper electrode, minus E0 zinc 2 plus becoming zinc. This is the standard reduction potential of the zinc electrode, right? And this is how we write standard cell potential. This is how we write standard cell potential. Okay, right? So this is the reduction potential of the cathode and this is a reduction potential of the anode. Okay, the difference of these two is what we call as cell potential, right? And this cell potential is actually we can measure by from the potentiometer. Okay, this is measurable, can be measured directly, can be measured directly. You can measure directly through experiment. Okay, but these two things can be measured in indirect manner. We are going to discuss that. Okay, see what I'm trying to say, student. When you join the two electrode and if you immerse salt bridge, everything, whatever potential that appear here, that appear in the potentiometer, this is nothing but cell potential or standard cell potential. Since we have taken 1 molar solution, the potential is standard cell potential. Students, standard cell potential we can measure directly through experiment, because whatever value appear here, that is nothing but standard cell potential. But the individual potentials of the electrodes, that we have to measure separately, indirectly. How to do that we'll discuss as we go along. But before that, let me introduce one more point, one more information, that is how to represent a cell on a paper. Okay, cell representation. This is very, very important one. Cell representation. How to represent a cell on a paper. Okay, we can't draw the cell like take one vessel and put one electrode, take another vessel, take electrolyte. We cannot draw every time like that. Okay, we have a shortcut method to represent a cell. What is the shortcut method? The shortcut method is this. First, remember this point. Put a double vertical line, parallel lines, right? This represents a salt bridge. Salt bridge. And always write anode in the left hand side and cathode in the right hand side. This is the first information you should keep in mind. If you want to represent a cell on a paper, this is IUPAC representation. Okay, this is as per IUPAC rule we are writing. Okay, if you want to write a cell, if you want to represent a cell on a paper, first put a salt bridge. In the left hand side always anode, and in the right hand side you should write always cathode. Okay, this is the first point. Then second important point, see in the anode or cathode side, right, if the species involved, species means reactant or any ions, right, whatever it is, species involved in the anode side or cathode side, if they exist in same phase, okay, at electrodes, I'll write simply at electrodes. At electrode mean anode or cathode. Anode or cathode. At electrodes, right, if species means the chemical entities which undergoes reaction, right? If species involved are in same phase, same phase means if all the species are gaseous, if all the species are liquid phase, if all the species in solid phase, right? If species involved are in same phase, if everything in same phase, then between the species you should put a comma, right? What is meant by that? Suppose I have a ferrous ion in aqueous solution and ferric ion also present in the same solution. Students, observe carefully. Now we have ferrous ion, ferric ion, both are present in the same solution. Since both are in the liquid phase, I should put a comma in between. Right? If species involved are in same phase, then between the species you should put comma. Okay, keep this in mind, very, very important. Then second point, if species involved are in different phase, then we must put a single vertical line in between the species. For example, listen, in the case of hydrogen electrode, if you use hydrogen electrode, we are going to discuss that, okay, where we use a platinum metal, we use a hydrogen gas, and the hydrogen gas is passed through an H plus ion solution present in the liquid, aqueous H plus ion. See, this is liquid, this is gas, this is a solid. To represent this electrode, we must put a single vertical line in between. It is called phase boundary. Students, single vertical line indicate phase boundary. And remember this order always. Suppose if salt bridge is here, right, close to the salt bridge, always we keep solution in the liquid phase or species in the liquid phase. Species in the solid phase always present, right, far from the salt bridge. What is the meaning? Yes, we will discuss. I'll give with some examples so that you can easily understand this, right? Students, any doubt up to this? Okay, right. Now I'll show you how to represent Daniell cell on a paper. Right? How to represent Daniell cell. How to represent Daniell cell on a paper. It's very simple actually. Listen, first I'll put a salt bridge. Students, observe carefully. First I'll put a salt bridge. Then in the left hand side we should write anode. Okay, anode, see, you have zinc rod immersed in zinc sulfate solution, right? So zinc rod is solid, zinc sulfate solution is a liquid phase, so you have two different phases, therefore you must put a single vertical line. So I'll put zinc solid and put a single vertical line. Then zinc sulfate solution, actually the zinc ion take part in the reaction, so I'll write only zinc ion in aqueous medium. What is the concentration? Concentration is 1 molarity. You can also write the concentration of the species if it is available. Then in the right hand side we should write the cathode. This is anode, left hand side anode, right hand side cathode. In the cathode side we have copper rod immersed in copper sulfate solution. Okay, always write the solid far away from the salt bridge. So write the copper solid at the terminal position. Okay, then place copper sulfate. Actually the cupric ion is taking part in the reaction. I'll put cupric ion here, and this is also 1 molar, so I'll write 1 molar here, 1 molar solution, right? This is how we should represent the cell. Okay, and whatever potential that is produced, see, we have taken 1 molar and 1 molar, therefore this is a standard cell. Okay, this is actually a cell in which the potential produced is called standard cell potential. And what is the potential produced in this cell? E0 cell equal to 1.1 volt. You know very well. The potential produced from a Daniell cell is 1.1 volt. Students, 1.1 is the maximum potential that is offered by the Daniell cell. Maximum potential. Okay, if you purchase Daniell cell from any battery shop, okay, it was written that 1.1 volt. It means the fresh battery will produce 1.1 volt, but as the days progress, okay, the voltage slowly drops. Okay, now listen, student, observe carefully. This is the idea. Now what is the meaning of this? Why we write like this? If you write like this, then it is very easy to write the cell reaction. What is the meaning? What I'm trying to say? Listen, what is cell reaction? Here at the anode, zinc is becoming zinc 2 plus ion, correct? It is undergoing oxidation. So what is the oxidation reaction? Zinc, right, lose 2 electron and become zinc 2 plus ions. This is the reaction occurs at the anode, right? And here this is solid phase and this is in aqueous phase. And what happened here in the cathode side, cupric 2 plus ion, cupric ion undergoes reduction and become copper. So just remember this arrow mark. Always this arrow mark, okay, goes in this manner. Cupric ion here become whatever may be the cell. Always the arrow mark should be like this, right? So in the cathode side, cupric ion in aqueous medium gains 2 electron and become copper solid, right? So this is the reaction occurs at the anode and this is the reaction occurs at the cathode. We can write directly by saying the cell. Okay, then what is the overall reaction? What is the overall reaction? Overall reaction is sum of these two. Okay, students, while writing overall reaction, see the number of electron in both the sides. In this case, number of electron in both the sides are same. So you can just cancel the two electrons and add the left hand side quantity and right hand side quantity and write as such. So I'll write like here, zinc solid plus copper cupric ion in aqueous medium giving zinc 2 plus aqueous plus copper solid. This is the cell reaction occurring in the cell. Students, observe carefully. This is the cell reaction occurring in the cell. Take down. So this is how we should write the Daniell cell. We should Daniell cell on a paper, and this is the reaction occurring in the cell. Zinc undergoes oxidation and copper undergoes reduction. Okay, now let me give one or two examples and I'll explain how to do this. How to write a cell on a paper. Then students, now see, I'll give a cell, right? See, copper solid immersed in cupric ion aqueous medium, salt bridge. Then silver solid immersed in Ag plus solution, right? Solution containing silver ion. Now I have given a cell, right? If you write a cell on a paper like this, what is the meaning? This is salt bridge and this is the anode part, anode half cell. We say that the full arrangement is one full cell, complete cell. This half is the one half cell and this is another half cell. So a cell consists of two half cells. One is anode, the other one is cathode compartment. Okay, so in the anode compartment, we have copper immersed in copper sulfates or cupric ion solution. In the cathode compartment, this is the cathode. In the cathode compartment, silver is immersed in silver ion solution. Now, students, observe carefully. We always write anode in the left hand side and cathode in the right hand side. Now, what is the cell reaction? Yes, how to write the cell reaction, student? Very simple. Just see this arrow. Copper becoming copper 2 plus and silver ion becoming silver. Okay, so what is the reaction occurs at the anode? At anode, copper solid undergoes oxidation and become cupric ions in the aqueous medium and release 2 electrons. And what happens in the right hand side? In the right hand side, silver ions present in the solution phase gains electron. Each silver ion gains 1 electron and becomes silver solid. Right? This is the reaction occurs at the cathode. Now I am going to write the overall cell reaction. But while writing cell reaction, students, observe carefully, number of electrons should be same. In the anode side, we have 2 electrons released, whereas in the cathode reaction, we have 1 electron consumed. Therefore, what I am going to do, I am going to multiply this reaction throughout by 2. So if I multiply by 2, I will get 2 here, 2 here, and 2 here. Now number of electrons are same. Okay, so you have to cancel this and this. Now just add the left hand side and right hand side quantity and write as such. So copper solid plus 2 Ag plus aqueous giving copper 2 plus aqueous plus 2 Ag solid. Okay, so this is the reaction taking place in this cell, right? This is how we should write. This is how, if a cell is given, if a cell is given in cell representation, okay, you should know how to write the cell reaction. Now I'll tell you how to write the cell potential. Students, it's very simple. It's very simple. If cell representation is given, you can write the cell potential directly. See here. I'll write the standard cell potential first. Standard cell potential. Don't worry about whether the concentration is given 1 molarity or not. Standard cell potential you can always write directly. Okay, how? Standard cell potential is nothing but standard reduction potential of the cathode minus standard reduction potential of the anode. Simple. Alright, E naught reduction potential, standard reduction potential of the cathode minus standard reduction potential of the anode. Okay, and I have told you that always we write potentials, electrode, these are all electrode potential. Cathode is an electrode, anode is an electrode, therefore this is an electrode potential, this is also an electrode potential. Always we write electrode potential as reduction potential. So it is not necessary to write reduction here, it's not necessary. Okay, so I can write simply E naught right minus E naught left. What's the meaning? Why right and left? Because according to cell representation, we always keep cathode in the right hand side and anode in the left hand side. That's why I wrote simply E naught R minus E naught left. Okay, so this will give you standard cell potential directly. Right, take down. So if you want standard cell potential, student, you need not worry about the reaction and all. Right, reactions are not necessary. You can write directly because these values, right, are standard values, they are available already. Okay, take down. I'll show you how to calculate standard cell potential for a cell using the electrode potentials. Right? Yeah, this is actually quite simple. I'll give 1 or 2 examples so that you can easily understand how to calculate the standard cell potential. Right, so remember this formula. Always the standard cell potential formula is E naught right minus E naught left. That's all. Okay. Now, I have told you for Daniel cell, the standard cell potential is 1.1 volt. How? How did I get that? How did I write that value? Yes, I'll show you. Let me show you the E naught cell potential values once again for different electrodes. The standard electrode potential values, right, are already available. Okay, I'll just show you a book. This is this book is the famous book. I'll just show you the book name, Chemistry by Raman Chang. Okay, this book was written by Raman Chang. It's one of the very good book for to understand the basics of chemistry. Right, now listen here. In this book, cell potential values are given here. Right, these are all cell potential values. Right, now in this cell potential value, okay, standard reduction potential for zinc, copper, right, for many electrodes potentials available here. So I'm going to choose values from this table and I'm going to show you how to calculate standard cell potential for Daniel cell. Okay, so I'll take this one first. Number 1, students observe carefully. Zinc solid immersed in zinc ion solution, aqueous, cupric ion solution in which copper rod is immersed. This is Daniel cell. Okay, you know very well. Zinc immersed in zinc ion solution, copper immersed in cupric ion solution. This is standard cell. I'm sorry, Daniel cell. Students, observe carefully. What is the standard reduction potential? Because I have told you we must use only reduction potential. What is the reduction potential for anode? Reduction potential means zinc 2 plus becoming zinc. This is reduction. Okay, reduction potential value, right? I am just taking the value from the table, but in the examination they will provide the value actually. Right, all the values will be provided. So right now I will take the value from the table. The value for zinc is minus 0.76 volt, minus 0.76 volt, right? And the reduction potential for copper, Cu2 plus becoming Cu, for the reduction potential for copper is the values available. It is plus 0.34 volt. Students, I have taken the value from the standard potentials available, standard reduction potentials available. Okay. Now students, these two values they will provide in the examination. They will provide this value. Now how to calculate standard cell potential? For standard cell potential you need not worry about the cell reaction, but I have taught how to write the cell reaction, okay, and all. And now I am going to show you how to calculate standard cell potential. Right? What to do? Right hand side reduction potential minus left hand side. So right hand side we have copper. For copper the reduction potential is given, which is plus 0.34 volt. Then put a minus sign. Then for zinc the reduction potential is available, minus 0.76 volt. Students, observe carefully. This is the reduction potential for copper. Then this is the reduction potential for zinc. Zinc becomes zinc 2 plus, right? For that reaction this is the reduction potential. Now what is the cell potential? This minus this value. Right hand side value minus left hand side reduction potential values. Keep this in mind. Always we must use reduction potentials for electrodes. Okay. Then so this is 0.34. Here minus or minus become plus 0.76. So if I add these two, we'll get 0, 1, 1. So we'll get exactly 1.1 volt. That's why I told you the E0 cell for a Daniell cell is 1.1 volt. Standard cell potential for Daniell cell is 1.1 volt. Okay, take down. Students, is this clear? Any doubt? Any doubt?
No doubt, sir.
Yeah. Now I will give a cell. You try to calculate the standard cell potential. Okay. Yes. Now I'll give you a cell, and I'll give you the standard cell potentials values also. Right? I'll give. Aluminium solid immersed in Al3 plus aqueous solution, salt bridge. Here we have zinc, copper 2 plus aqueous copper solid. See, I have given a cell, right? And the standard electrode potential values I will provide. E0 Al3 plus becoming Al, then E0 copper 2 plus becoming copper. Students, I am giving you only the reduction potentials. Even in the examination, right, most of the time they will provide reduction potentials. Very rarely they will give oxidation potential. If oxidation potential is given, you need to change it into reduction potential. That's all. How to change? Very simple. Just change the sign of the value. Okay. So for aluminium, the potential available is minus 1.66 volt. Okay, and for copper we know the value already. Anyway, I'll give once again plus 0.34 volt. 34 volt. Now the question is this: calculate the standard cell potential. Yeah, students, do it fast. I'll be back in 2 minutes. Yes, students, can you tell me the answer?
Just a minute, sir.
Yeah.
1 minute, sir. Sir, the answer is 2 volts, sir.
Answer is yeah. Yes, you're right.
2 volts.
Yeah. See, very simple, ma. E0 cell is nothing but right hand side reduction potential, right? Reduction potential of the right hand side electrode minus reduction potential of the left hand side electrode. Okay, you must use only reduction potential, I have told you. And here reduction potential only given. So for right hand side we have copper, right? So for copper 2 plus becoming copper, the potential is 0.34 volt, 0.34 minus. For left hand side, the reduction potential is given minus 1.66 volt. Okay, so this is 0.34 minus of minus is plus 1.66. If you add them, you will get 002. So you will get 2 volt. So this cell, okay, this that is this cell, right, can produce 2 volt, maximum of 2 volt when you use standard condition, right? Take down. Is this clear? Any doubt?
No doubt, sir.
Yeah, right. So this is how we should calculate the standard cell potential. Remember, to calculate standard cell potential, you need not worry about the chemical reaction occurring in the cell. Cell reaction is not necessary at all. Okay. What is required? The standard reduction potentials of the electrodes are required. Okay, they'll provide reduction potentials of the electrodes, right? That is what important for standard cell potential, right? But later I'm going to discuss about cell potential. To calculate cell potential, right, you need both the datas. Okay, you need standard reduction potentials of the electrodes, and you also require the chemical reaction. What chemical reaction occurring in the cell? Both are required. To calculate standard cell potential, okay, only the reduction potentials of the electrodes are required. Right? Chemical reaction is not important. Right? Keep this in mind. Now, so I have introduced this. Now I'll give a cell. You try to write the cell reaction occurring in the cell. Okay. I'll give a cell. Okay, let me provide a cell. Chromium, I'll write here. Chromium solid immersed in chromium 3 plus aqueous solution, salt bridge. Here I'll write copper instead of copper. Okay, copper is the better example, so I'll write copper 2 plus aqueous plus single copper solid. Yeah, now the question is, calculate standard cell potential and also write the cell reaction. Both you have to do now. To calculate standard cell potential, reduction potentials are required. I'll give the values. E0, chromium 3 plus becoming chromium, it is called reduction, and the potential is reduction potential. The value of this is minus 0.74 volt, and the standard reduction potential for copper 2 plus becoming copper, okay, this is plus 0.34 volt, we know very well. Yes, calculate the standard cell potential and also calculate and also write the cell reaction. Yes, student, do it now. This is also quite a simple task, so you can easily do that. I will also write here. So to calculate standard cell potential, what we should do, this simple formula is E naught right minus E naught left, because cell representation is given, so you can write directly, right? So in the right hand side, what is the reduction potential of the right hand side electrode, which is given here, plus 0.34 volt. Students, observe carefully. Cu2 plus becoming Cu is reduction, therefore this potential is reduction potential. Chromium 3 plus becoming chromium is reduction, therefore this potential also reduction potential. Remember, both are reduction potentials, they always provide reduction potentials. Okay, so standard reduction potential of the right hand side electrode minus standard reduction potential of the left hand side electrode. Left hand side we have chromium, right? So this potential is given minus 0.74 volt. So what's the value? 0.34 plus 0.74. Yes, what's the value, students?
$1.08.
Yes, 1.08 volt. This is the standard potential, standard cell potential, right, available from this cell. Okay, now how to write the cell reaction? How to write the cell reaction? It's very simple actually. First you write the anode reaction. Say in the anode side, chromium become chromium 3 plus, right? Chromium become chromium 3 plus means it releases 3 electron. So I'll write here chromium solid becoming chromium 3 plus aqueous and release 3 electrons. Good. This is the reaction occurs at the anode. And what about in the cathode? In the cathode, copper 2 plus becoming copper. That means it gains 2 electron. I'll write here Cu2 plus aqueous gains 2 electron and become copper solid. This is the reduction reaction occurs at the cathode side. Now students, observe carefully. While writing cell reaction, number of electrons should be same. But here 3 electrons are released, here 2 electrons are consumed, so it is not equal. So what I'm going to do, I'm going to multiply throughout this by 2, and I'm going to multiply throughout of this reaction by 3. So if I multiply by 2, I'll get 2 here, and 2 into 3, it becomes 6. Similarly, if I multiply this throughout by 3, I'll get 3 here, 3 into 2, 6, and 3 here. Now I'll sum up. So 6 electron cancels. So what we have in the left hand side is 2 chromium solid plus 3 Cu2 plus aqueous, giving 2 chromium 3 plus aqueous plus 3 copper solid. This is the overall cell reaction. Right? Is this clear, student? Any doubt?
No, sir.
Yeah, right. Take it. You must know how to write a cell reaction, and you must also know how to write, how to calculate the standard cell potential. Okay, take two. Right, then the next important point we have to discuss is that, see, I have told you we can measure the cell potential, right? We can measure the cell potential, or we can measure the standard cell potential, okay, directly from experiment. You can measure experimentally. Experimentally measurable. Okay, I have told you in the beginning, whatever potential that appear in the potentiometer, that directly gives you the cell potential. Simple. Cell potential or standard cell potential you can measure directly. Now the question is, what is the reduction potential of the electrode? Okay, standard, let me first start with standard reduction potentials. Standard reduction potentials, potential of electrodes. Students, observe carefully, I am using a different pen. Standard reduction potentials of the electrodes. How to calculate this? That's the question. This you can measure. Standard cell potential you can measure. How to measure standard reduction potentials of the electrodes? Okay, see, we write normally like this, right? E naught cell is nothing but E naught of the right hand side electrode potential minus E naught of the left hand side electrode potential. We write normally like this. Okay, so let this value be x and this value be y. X minus y is this. So x minus y value is E naught cell. Okay, this you can measure. Only the difference you can measure. You cannot measure what is the value of x and what's the value of y directly. Okay, that is, individual electrode potentials cannot be measured directly. I'll write here. Individual electrode potentials cannot be measured directly from experiment. Cannot be measured directly. You cannot measure it directly. Okay, right? So we can only measure the cell potential. We can only measure the cell potential or standard cell potential. We cannot measure the electrode potentials. Okay, so in order to measure the electrode potentials, people have given some idea. What's the idea? You can use reference electrodes. Okay, what is meant by that? See, we know only the difference. Okay, suppose I'll take x minus y equal to E naught cell, where x is the reduction potential of one electrode and y is the reduction potential of another electrode. We don't know what's the value of x, we don't know what's the value of y, but we know this value. Difference is available. Okay, only difference can be measured. But to find the individual value, what to do? Okay, what scientists did was they fixed potential for one particular electrode, okay, as 0. They fixed it and they considered that electrode as a reference electrode. Okay, so they introduced what is called the reference electrodes. Reference electrode. For reference electrode, okay, they have assumed some potential. Okay, we are using two reference electrodes actually. Number one, standard hydrogen electrode. Standard hydrogen electrode, and second one is calomel electrode. Calomel electrode. We say that this is primary reference electrode. It is called primary reference electrode. I'll just put RE, reference electrode, and this is called secondary reference electrode. Actually, standard hydrogen electrode is the reference electrode, but every time constructing hydrogen electrode is difficult because we have to use hydrogen gas and all, which is difficult. So because of that reason, people have introduced the calomel electrode. Okay, we have two electrodes, okay, two reference electrodes available, so keep this in mind. But we are going to learn only standard hydrogen electrode here. Standard hydrogen electrode, which is used as the reference electrode. Okay, so we are going to understand how what is standard hydrogen electrode and how it is working. Okay, so SHE. What is SHE? SHE is a short form. Okay, standard hydrogen electrode. Right? It's a simple apparatus where we take some solution in a container. We'll take some solution, aqueous solution, which contain H plus ions. You should take solution containing H plus ion, and the concentration, students often see nowadays we are using just concentration, but actually we should use activity. Okay, activity of the H plus ion should be equal to 1, or if, we can also say that concentration is 1. If H plus ion concentration is 1, then I'll immerse a glass tube like this. A glass tube, right? And at the center we have an electrode, that is the platinum electrode. It's a platinum electrode. Right here we have wire connection, and there is a valve. There's a valve here. Through this valve we pass pure and dry hydrogen gas. Okay, and here we have taken standard hydrogen electrode. I have told you, if it is standard, concentration should be 1 molarity or 1 activity should be 1. If it is standard, if any gases are used, the gas pressure should be 1 atmosphere or 1 bar. Okay, I'll put 1 atmosphere pressure. If pressure is 1 atmosphere and activity is 1, and if the solution temperature, this is actually not a standard condition, but by convention we use this 25 degrees Celsius. Okay, then the potential developed at this electrode, some potential is developing, no doubt in that. The potential developed at this electrode, it is called standard hydrogen electrode potential. Okay, and the value is this. Students, observe carefully. Observe carefully. We pass pure and dry hydrogen gas through this tube so that the gas bubbles. Right, the gas, you can see the bubbles coming out like this. Right, and what is the reaction takes place? If you use this electrode as anode, I'll write here. If you use, let me write the next page. If the electrode she means standard hydrogen electrode. If standard hydrogen electrode, if it is used as anode, if standard hydrogen electrode, okay, is used as anode, then what reaction takes place? Anode means oxidation. So what will happen here? Hydrogen gas or hydrogen molecule, right, undergoes release electron and becoming H plus ions. That H plus ion goes to the solution. This is the oxidation reaction occurs if hydrogen electrode acts as anode. And what is the potential? The electrode potential here, see student, here H2 become H plus ion, right? H2 become H plus. It is called oxidation. The standard oxidation potential is chosen arbitrarily as 0. Okay, the value is chosen as 0. Scientists fixed this value as 0. They have assumed it. Similarly, if you use standard hydrogen electrode as cathode, then what reaction takes place? H plus ions from the aqueous medium gains 2 electron and become hydrogen gas. This is the reduction reaction occurs at the electrode if standard hydrogen electrode is used as a cathode. And what is the reduction potential? The potential is H plus becoming H2. This is also 0. Whether you use standard hydrogen electrode as anode or cathode, the electrode potential is 0. That's the point you should keep in mind. Students, observe carefully. Standard oxidation potential for hydrogen electrode, standard reduction potential for hydrogen electrode, both the values are 0. Okay, so keeping this value, see this, actually this value is not 0. there may be some value, but what people did was to find the electrode, to find the individual electrode potential, they fixed the electrode potential for one of the electrode as 0. Okay, and they have chosen hydrogen for this purpose. So for hydrogen electrode, they have chosen the value as 0. Using hydrogen electrode, we can calculate the standard potential, reduction potential for other electrodes. Okay, that is very easy one. We'll do that in the next class. Okay, so remember student, this is very important point. Whether you use hydrogen electrode as anode or cathode, the standard potential of the electrode is arbitrarily chosen as 0. Take down. Okay. Yeah, students, any doubt up to this?
No.